This is video 1 of probably 3 for my DGD. This is for Calculus for the Life Sciences. I'll be using this textbook. This first video I'm going to review Chapter 2. This is by no means comprehensive. There are several ideas that may be left out. I only cover the key concepts. Okay, we'll start with Chapter 2, Discrete Time Dynamical Systems. And a discrete time dynamical system is represented as a value at time t plus 1 is equal to some function of a value at time t. And this function is what we call the updating function. And let's just give an example. This updating function is 2at plus 1. So our discrete time dynamical system in this case is at plus 1 is equal to 2at plus 1. And a discrete time dynamical system is always paired with an initial value. Otherwise, we don't really have that much interest in it. So let's say our initial value is 3 in this case. So we need to talk about a solution of a discrete time dynamical system. And a solution is just explicitly what our experiment is at each time. So at time 1, we double 3 and add 1, which gives us 7. And at time 2, we double 7 this time, and we add 1, and we get 15. And we want to solve this discrete time dynamical system for all t. Get an explicit function that when we plug a t in, it gives us exactly what it is at that time. And we know that linear functions have a form with arbitrary variables here. A times b to the exponent t plus c. And we're going to equate this function at time 0, 1, and 2 with the values that we actually calculated at that time to solve for these variables. There's sometimes you'll be able to see what this is, and b is almost always the number that we're timesing by, which in this case is 2. If you look at the examples in the textbook, they show you an intuitive way of doing it. I'm going to calculate it explicitly. So when we equate this new function to our 3 times, we're going to get system equations, 3 functions and 3 variables. So at 0 we get a times b to the 0 plus c, which is equal to a plus c, is equal to 3. That's our initial value. And then at time 1 we get a times b to the 1 plus c is equal to ab plus c, which is equal to 7. And we have a b to the 2 plus c is equal to 15. And now since we have 3 equations and 3 variables, you should have some practice solving these. What we do is we solve for c for 2 and 3, and we plug it into part 1. We should get these 2 equations. Then you create a ratio using these 2 equations. And over here you get 1/3. And so here the a's cancel, and you can use difference of squares down below. And what you're left with is 1 over 1 plus b is equal to 1/3, which implies that b is equal to 2. So b equals to 2 is what we expected. Go back to this equation here. So when we pull the a out, so a times 1 minus b is equal to -4. We plug the 2 in, we get negative a is equal to -4, which gives us a is equal to 4. We take a is equal to 4 and we plug it into the first equation, and that shows us that c is equal to -1. In conclusion, a function which describes this dt ds over time can be represented as 4 times 2 to the t minus 1. We know this equation is good and is going to work, but we want to verify that. And we do that by applying the updating function to it and showing that when we do this, it gives us the exact same function but at time t plus 1. And so the updating function doubles it. So we get 2 times 4 times 2t minus 2, and it adds 1. the 2 gets brought into to this with the exponent rule, so it becomes 4 times 2t plus 1, and you get minus 1, which is just this first function, but at time t plus 1, so we verified it. Updating functions. As you know, the updating function, when applied to the dtds at time 0, is then the dtds at time 1. If you apply the updating function twice under composition, you will get it at time 2. More generally, if you apply the updating function twice under composition at any time, you will get the dtds at at plus 2. And the number of compositions you do corresponds to how far along the dtds. For example, if you do 4 compositions of the updating function at time 3, you will get the dtds at 7. If we have a dtds, let's say f at, if we have an updating function for a dtds at at and it gives you, let's say, 3 at plus 1, it's of interest of us what the inverse updating function is. Luckily, the inverse updating function, we take a look at the discrete time dynamical system, and we solve for at. So first thing you do is subtract 1 from both sides, and then divide 3, and you're left with at. So the inverse updating function is thus at minus 1 over 3. Another concept that interests us are equilibrium points. Points where when we apply the updating function, it doesn't change. So we do this by equating the function to equaling the input. We want the input to be the output of this function. And then we can solve just algebraically. I'm going to subtract 3a star from both sides, and then I'm going to divide by negative 2. Means that f at negative 1/2 is equal to negative 1/2. Alright, so a short reminder on cobwebbing. Let's say our initial value is at 3, so we start here. First step is to go horizontally to the diagonal. And of course the diagonal will only be on one side, so you just go towards it, and you stop when you hit the diagonal. And then you go vertically to the updating function. And since the updating function is a function, it passes the vertical line test, and so it will only have one point on a vertical line. So we go towards that one point, which is right here. And now we just repeat the process from this new spot. So we go horizontally to the updating function, which will be on one side, and then we go vertically to the updating function. And since it passes the vertical line test, there's only one place to go. And we can do this for a couple more steps. Now, I don't have an explicit function for this graph that we're looking at here. It's a linear function with a negative slope, and where the updating function intersects the diagonal is an equilibrium point. And it's of interest to us that this is, since we're traveling away from it, an unstable equilibrium point. If we were going the other way, then it would be a stable one. We're spiraling away, so it's unstable. If we were spiraling towards it, it would be stable. Now you don't need to spiral to get a stable or unstable point. You just have to either approach it, which means it's stable, or go away from it, which means it's unstable. Exponential dtds's are of the form at plus 1 r times at. And these have a quick and easy solution if you want a function of the solutions over time. Let's just call them ht is equal to rt times the initial value. say we have the question where our per capita production is 1.5, which is the R in this equation, and our initial value is 3, and the question is what time in our DTDS do we need to reach 100? So we take this equation and we want to reach 100, so we set h of t to equal 100, 1.5 to the t times 3, and we want to solve for t. And in these situations we want to get the t down, so what we do is first divide by 3. So we have 100 over 3 equals 1.5t. Then we use the ln function in order to solve for this. So ln of 100 over 3 is equal to t times ln of 1.5, and this is the exponential ln rule. Review your ln rules if you're not familiar with them. And then we just divide ln 1.5. So we get t is equal to this number. So we get that t, when we use our calculator, is equal to 8.6 blah 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 blah. We need to reach 100. And our discrete time dynamical system is only defined for whole numbers. So we take the next thing. We take t is equal to 9 will suffice.